how to upload to IPFS and work with IPFS ourselves. So let's go ahead and do this. So let's create a new file in our contracts and we'll call it advanced collectible.sol. And what we're going to do here is we're going to make, again, an NFT contract where the token URI can be one of 3 different dogs. So if we look at this NFT mix in the images section, there's a pug, a Shiba Inu, and a Saint Bernard, or one of these 3 dogs. We're going to make it so that when you mint one of these NFTs, you're going to get a random one of these 3 dogs. Now, I'm not going to go over stat generation and like creating battling NFTs or really games out of these NFTs. If you guys want to see a version of those contracts, check out this Dungeons and Dragons NFT. There's a link in the GitHub to see this, and it actually creates characters that can do battle and have like stats and attributes like attack, constitution, and different things you'd find in Dungeons and Dragons. This one's done actually with Truffle as opposed to being done with Brownie, but all the contracts are going to be the same other than this migrations.sol. So if you're looking to check this out, you absolutely can. It is a ton of fun. And they have some really cool images as well. So be sure to check that out if you're looking for more. Anyways, here's what we're going to be looking to do. We're going to make an NFT contract where the token URI can be one of 3 different types of dogs, and it's going to be randomly selected. So let's go ahead and do it. So first, again, we're going to do this SPX license identifier right at the top. So we can go ahead and put that there. And we're going to even use same Solidity version, and we're going to use Open Zeppelin again. So we can literally just copy and paste that from our last project. Now we're going to create our contract, advanced collectible. We're going to say is ERC 721. Great. And then, since we're going to want to work with Chainlink VRF to get a provably random NFT, we're also going to want to import at chainlink/contracts/src v0.6 VRF consumer base.sol. And of course, that means we're going to go back to here and we're going to add smart contract kit /chainlink brownie contracts at 1.1.1. And then we're going to go ahead and add the remapping in. We'll say at chainlink equals, boom. Awesome. So we've imported the Chainlink bit. Our advanced collectible is ERC 721, and it's going to be VRF consumer base. So same as always, let's go ahead and start with the constructor. We know from our lottery smart contract that we're actually going to want to parameterize a lot of these pieces for working with the VRF coordinator for working on different chains and different test nets. So we're going to do address VRF coordinator. We're going to do address link token bytes 32 key hash. And we can always head back over to docs.chain.link, go to get a random number just in case we forget what some of the parameters are. VRF coordinator, link token, key hash, and fee. Great. You went 256 fee. And we'll make this public as well. Add a little curly bracket there. And we can go ahead and start doing the rest of this. Of course, we need to do the VRF consumer base constructor and the ERC 721 constructor. So VRF consumer base is going to be this VRF coordinator and this link token and the ERC 721. We could parameterize these as well, but we know it's going to be a dog, so we'll do doggy and the symbol of dog, which is the same as our simple collectible here. We know we're also going to need to do this token counter bit. So we'll do UN256 token counter. And right in here, we're going to do token counter equals 0. Of course, we're going to need a key hash. So let's make this UN256 public token counter. Excuse me. We're going to do a bytes 32 public key hash. And we're going to do a UN256 public fee. And we'll set key hash equals key hash and fee equals fee. Great. So this is a combination of a lot of the stuff we did in our lottery smart contract and some of the pieces that from our ERC 721. We need the key hash, the fee, VRF coordinator, link token, all for the VRF consumer base. Oops, I should put an extra quote here. And then we need dog, doggy, and a token counter for our ERC 721. So now we're going to create our function create collectible. So we're going to do function create collectible. And again, we're going to do a string memory token URI. But this time in our Python scripts, we're actually going to define where we're getting this token URI from, and we're going to create it ourselves. But we're going to make this public, and it's going to return a bytes 32. Remember way back in our lottery, when we did this event requested lottery winner, when we called the chainlink VRF, we're going to do a similar thing here where we're going to make an event for whenever we request one of these new dogs. And that is also what we're going to return. We're going to return that request ID here. So since we're using the chainlink VRF here, we can go ahead and call that request randomness function, which again, head over to the docs.chain.link. This is imported from the ERC 721. And then in that request and receive model, it's going to call back with our fulfill randomness function. We're going to need to do a couple of different things here because we want the user who called to create collectible to be the same user who gets assigned the token ID. So first we'll do bytes 32 request ID equals request randomness. And we're going to pass obviously the key hash and the fee. This is going to create our randomness request to get a random breed for our dogs. So let's go ahead and just define a little bit of the fulfill randomness function so we can figure out how we're actually going to pick a random dog. Well, the first thing that we're going to need is we're going to need some definition of what the different breeds that the dog can actually be. And again, similar to the lottery, we're going to create a new type called breed using the enum. So we're going to do enum breed, and then we're going to give it 3 types. Pug, which is going to be state 0, Shiba Inu, which is going to be state 1, and Saint Bernard, which is going to be state 3. So our breed is going to be one of these 3 breeds here. So then in our function fulfill randomness, when we get that random number back, we can use that random number to pick one of these 3 breeds. So of course we need to have a bytes 32 request ID and uint256 random number, and we're going to make this internal override so that only the VRF coordinator can call this. And what we're going to do now is we're going to select a breed based off of this random number. So we're going to say breed, which we're saying this breed variable is of type breed. It's going to be equal to breed generated from that random number mod 3. Since we have 1, 2, 3 different breeds. Awesome. So this is how we're going to get our random breed. However, we do need to assign this breed to its token ID. So now that we have a random breed back, how do we actually go ahead and assign this? Well, we're going to have to create a mapping to do this. It'll look something like token ID to breed. We're going to have to get our token ID somehow, and we're going to have to equal it to the breed. So then our first question is, okay, well, in order for us to assign this breed to the token ID, how do we actually get the token ID? Well, we're going to grab the token ID by doing uint256 new token ID equals token counter. And then we'll just set the token ID to breed using this new token ID equal to the breed. So we're going to want to make this token ID to breed mapping up here, to which we can do mapping uint256 map to breed, and we'll call it token ID to breed. This way, each token ID is going to have a very specific breed based off of this mapping's results. Perfect. Okay, what else do we need in this fulfillment? We need to mint the NFT, and we need to set a token URI. Well, when we minted it before, we called this safe mint function. However, message.sender here is always going to be the VRF coordinator, since the VRF coordinator is actually the one calling this fulfill randomness. So we can't actually have this just be message.sender. We need to figure out how we can get the original caller of create collectible here. How do we get the original message.sender of create collectible? Well, the answer there is actually going to be in another mapping. When we call create collectible, we can create a mapping of request ID to sender. And this is going to take the request ID as a key and then whoever sent it as the value. So we're going to create this new mapping at the top. And then actually let's make this other mapping public as well. We'll do mapping bytes 32 to address. And we'll call this public request ID to sender. Now in our fulfill function, the same request ID that requested the random breed is returned. So what we can do is we can say address owner or sender is going to equal request ID to sender of request ID. And then this address owner is who we're going to safe mint the NFT to. And of course, while we're matching up the functions, we don't want to forget to always do token counter equals token counter plus 1 at the end. Awesome. Now we still need to set the token URI here. So back in our advanced collectible, we're going to have to do this set token URI at some point. So let's actually think about this for a second. We're only going to know breed of our dog once this random number is returned. And we know the breed of the dog is going to be one of these three breeds. It's going to be a pug, a Shiba Inu, or a Saint Bernard. And let's actually, for now, let's even just go ahead and add those three images to our project here. Create a new folder. We'll call it image. And you can put whatever images you want in here. I'm actually just going to download the three images right from the NFT mix. Boom. And now I have my pug, my Shiba Inu, and my Saint Bernard in here. So anyways, it's going to be a pug, Shiba Inu, or a Saint Bernard here. We're only going to know what the breed is once the random number is returned. And the breed is actually going to govern if it's a pug, Shiba Inu, or a Saint Bernard. So we technically could actually just get rid of the input parameters for create collectible, since there's going to be no token URI initially created. What we could do is we could create a new set token URI function that sets the token URI based on the breed of the dog. For the simplicity of this project, we're actually just going to create our own set token URI function that we're going to update based off the breed of the dog. A challenge for you after we finish this project is to make this even more decentralized and have the fulfill randomness function actually be the one to decide what the token URI is. But for now, in our fulfill randomness function, we're going to skip setting the token URI, and we're actually going to call it in a separate function. We're going to create our own function called set token URI. And we're going to pass it a uint256 token ID, a string memory token URI. And we're going to make this a public function. Once this fulfill randomness function is responded, the breed of the dog is going to be set, right? This token ID to breed is going to say, hey, this token ID now is associated with this breed, which is going to be pug, Shiba Inu, or Saint Bernard. All we want to do then is, now that we have the on-chain metadata, we're just going to reciprocate that with the off-chain metadata. So we're going to need 3 token URIs for those 3 dogs. We're going to need one for pug, Shiba Inu, and then obviously Saint Bernard. However, we want to make it so that only the owner of the token ID can actually be the one to update the token URI. So we can use a require function for this. We can say require, and we're going to use an imported OpenZeppelin function called isApproved or owner message sender token ID. And we're going to do a comma here, ERC721 caller is not owner nor approved. This is approved or owner function, if we go into the ERC721 GitHub for OpenZeppelin, we can find this function is approved or owner, which checks the owner of the ERC721 of that token ID. And it makes it so that only the owner or somebody approved to work with this token ID can actually change the token URI. So then we're just going to call that function called set token URI of the token ID and the token URI. Now we're actually manually going to be the ones to call this set token URI once the breed has been decided. We could, of course, like I said, use a mapping at the top that automatically routes it there, but so that we can experiment a little bit more and learn a little bit more about IPFS, we're going to leave it a little bit more general like this. And perfect. This is pretty much the majority of what we're going to need for our ERC 721 contract. Obviously, we still need to work with IPFS and getting our token URI, but for the most part, this is everything that we need. Now, I am going to introduce a new best practice here. Whenever we update a mapping, typically a good best practice is going to actually be to emit an event. So let's create an event for each one of these mapping updates. We'll call it event requested collectible, and we'll do a bytes 32 indexed request ID, and we'll also do a address requester. This requested collectible event is going to be emitted when we request ID to sender because we're updating the mapping here. This is also going to be really helpful when we run our tests so we can get this request ID, similar to what we did with the lottery. So down here, we're going to do emit requested collectible. Let's collectible here. Let's use an I instead of an A here. Collectible. And we'll pass it this request ID and then message.sender. We also update a mapping down here with token ID to breed. So we're going to do a new event. We're going to call event breed assigned. And we'll do a uint 256 indexed token ID. And then we'll do a breed. And then when we assign the breed here, we're going to emit breed assigned with new token ID and breed. So let's see if we did everything right. Let's do Brownie compile. Looks like we have a quick error here. Did you mean fee or fee? Let's do a quick underscore there. Now let's try to compile. Much nicer. All right, great. Let's move on. All right, so now let's take a little look-see at our scripts here. So we have this deploy and create script, which is going to work for our simple collectible. So let's go ahead and actually give them both their own folder. So we're going to do a new folder. We'll call one simple collectible. And we'll do another new folder called advanced collectible. And we'll grab this original deploy and create and we'll place it into this simple collectible folder here. Awesome. Now, if we wanted to run this, we would do Brownie run scripts, simple collectible, deploy and create, and we can go ahead and test this out on our local ganache here. And cool, looks like it's working correctly. Great. So now let's create our advanced collectible script. And a lot of what we're going to do is going to be the same as this simple one, deploy and create. So I'm actually going to copy this. We're going to create a new file called deploy and create.py. We're going to paste everything in here. But we are going to change a couple things up. So let's do a little bit of refactoring first. So this OpenCRL, we're going to be accessing in a couple of different scripts. So we're actually going to take this, copy it, get rid of it in our deploy and create here. And we're going to move it to our helpful scripts and place it under here. OpenCRL equals this script right here. And now what we do in our simple deploy and create is we're going to do from scripts.helpful scripts import OpenCRL. We're going to delete that here. So now in this script, this OpenCRL is going to come from our helpful scripts, which is what we want. And we're going to do the same thing for our deploy and create for advanced. Okay, great. So I've now copied and pasted all the code from deploy and create into this deploy and create for our advanced collectible. So let's go ahead and modify this now. So instead of from Brownie import simple collectible, we're going to import advanced collectible. And we're going to do the same thing down here. And I'm even just going to go ahead and delete everything before this. We're going to change this to advanced collectible. And awesome. Okay, this is going to be our starting point. And we can even get rid of this sample token URI. Great. So this is going to be our new starting point. We've done a little bit of refactoring. Now OpenCURL is going to be in the helpful scripts. We're pulling an advanced collectible instead of simple collectible. And the rest applies. We're still using our get account to get the account. And now we have this advanced collectible equals advanced collectible dot deploy. Of course, our advanced collectible has a different constructor. It's got a VRF coordinator, a link token, a key hash, and a fee. So we're going to have to add those as the parameters in here. We want to work with Rinkeby for this because the OpenSea marketplace right now for testnets only works with Rinkeby. So that's why we're going to work with Rinkeby here. So let's get started and just grab those Rinkeby addresses first. So our advanced collectible needs a VRF coordinator and a link token. So if we head over to the Chainlink documentation, we go to contract addresses for the VRF. We can scroll down to Rinkeby, grab the VRF coordinator here, and same as before, we'll jump into our Brownie config. We'll do networks, Rinkeby, and we'll do VRF coordinator. We're also going to need the link token here. So we'll do link token. We need the key hash. And we need the fee, which is going to be 0.1 link, which we can do fee as 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, which is going to be 0.1. You can, of course, just copy and paste Brownie configs over to different projects because these values are always going to be the same. Now in our advanced collectible deploy and create, we can go ahead and add those variables in here. Since we're going to be interacting with actual contracts that are on chain, and we're going to want to be able to flip back and forth between the mock versions of them, we're going to bring back that get contract function that we used before. This is the function that's going to be smart enough to know if we need to deploy a mock or just grab from an actual contract. I'm going to show a little fast forward of me rebuilding this function, but feel free to copy and paste it from our last project. Now, something that we do need to talk about though is our deploy mocks function. The syntax here is going to be basically exactly the same. However, we do need to deploy a couple of mocks. So make sure you have these in your deploy mocks function. Specifically, we're going to need a mock link token and a mock VRF coordinator. And again, feel free to just grab these from our last projects. And then, of course, be sure to add your contract to mock dictionary, where the link token is mapped to the link token, and the VRF coordinator is mapped to the VRF coordinator. If you guys look in the GitHub repo, there's a couple try catches there that just make it a little bit nicer for error handling. But this is basically the entire script. So now what we can do, we can go back to our advanced collectible deploy and create, import this get contract from our helpful scripts, and we'll just replace this with get contract VRF coordinator. Get contract link token. And then for key hash and fee, since these don't really matter, these can be whatever we want, and these aren't really contracts, we can go back to our config. We'll add the development network, and we'll just add key hash and fee. And again, since it's just testing, we can just go ahead and make them exactly the same as Rinkeby. Whew, done a lot of work. Now, let's go ahead and run this on the development network again. So we'll do Brownie, run scripts, advanced, deploy and create, no network, so it's going to default to development. Let's see what happens here. And awesome. So we can see we actually did a couple of things here. So first, we deployed this mock link token. Then we deployed our mock VRF coordinator. We finished that, and then we deployed our advanced collectible all on a local network. So let's go ahead and continue here. Once we deploy this code, we're going to want to fund this contract with some link. The reason we're going to want to fund it with some link, of course, is so that we can call the random number. I like to have my funding with link also in a function. So we'll do fund with link, and we'll give an address, advanced collectible.address. And let's go ahead and create this function in fast forward.
We're going to fast forward this as well, but feel free to copy and paste your fund with link functions from past projects. Or if you want to slow this down and follow along, feel free to do that too.
Let's go back to our deploy and create. We now have this fund with link that we're going to do right here. And then all we have to do now is call our create collectible function here. So we'll just do advanced collectible dot create collectible. Of course, from account. And we'll do creating TX. We'll wait one block confirmation. And then we'll print new token has been created. So we are definitely going to want to test this because we have a number of custom scripts here, right? So let's go ahead and just do a manual test. So we'll do Brownie, run scripts, advanced collectible, deploy and create, and we'll do it on a development network. Whoops, we got to add Ether here. Sorry about that. In the Web 3.2a 1 Ether. So let's go ahead and run the script again. And all right, it looks like everything worked. Everything was deployed, new token has been created. Great, this is fantastic. Now, ideally, before we do an integration test, we would of course write some tests.
But I want to teach some things that are easier to demonstrate on an actual testnet. So we're going to go ahead and deploy this to an actual testnet before we write our tests. So we're just going to run the script again
and do -- network rank B. And awesome, a new token has been created. So what we can do is we can grab the contract address once again. We'll paste it into the rank B Etherscan, and we can see everything in here. We can see we've given it a little bit of link. We can see our two function calls. One is going to be the contract creation. One is going to be create collectible. Our contract has already been auto-verified, actually, because I verified this contract on rank B already, and Etherscan says, this bytecode is the exact same of another contract that we've already verified. And if we go to read contract and we go to token counter, we'll see one token has been created. We've actually created our first token. Now what we can do in our advanced collectible scripts, we can create a new script and just call it create collectible. .py. And in here, we'll just create a collectible. So all we have to do is we'll do def main per usual. We'll have to do from Brownie, import advanced collectible. We'll import account from our helpful scripts. We'll import fund with link. And in our main function, we'll do account equals get account. Of course, we need to import this as well from our helpful scripts. Then we'll do advanced collectible equals advanced collectible -1, because we just want to get the most recently deployed. We'll fund this contract with link. So we'll do advanced collectible.address. And we'll also choose an amount here. We'll just do web 3.2way of 0.1 with Ether. So that means we also have to do from web3 import web3. Then we'll do transaction. Then we'll do creation transaction equals advanced collectible dot create collectible from account. We'll do creation transaction dot wait. We'll wait one block confirmation, and then we'll print collectible created. Oops, sorry, I actually don't have to import account here, or accounts, excuse me. And sorry, this actually needs to be amount equals, excuse me. Now let's go ahead and run this. And what we're going to do is we're going to fund our advanced collectible with link, which is 0.1 link. And then we're going to create a new NFT. Awesome, collectible created. So if once again, We take this address, go back over to Etherscan, do a quick refresh here. We go to our contract, read contract. We look at the token counter. It may still be 1, so you might have to give it a second for the Chainlink VRF to respond. Once the Chainlink VRF responds, we'll see 2 in here. We can also check the token ID to breed. If we look at the 0th one, we'll see the breed is 2. And if we look back at our contract, the advanced collectible.sol, we know that if the breed is 2, that means it's a St. Bernard. See the token ID of 1, it has a breed of 1, so it got randomly assigned a Shiba Inu. Awesome. So we have tokens and they get randomly assigned breeds. Fantastic. As you can see, we're doing kind of a lot of manual testing work here, right? So what we're probably going to want to do instead is, you guessed it, automate these tests. Now we can go ahead and want to deploy advanced collectible. So we can go ahead and import that deploy script that we just wrote. So we would do from scripts .advanced collectible .deploy and create, import deploy and create. And then all we have to do is call deploy and create. In this function, we'd probably want to then return the advanced collectible contract so we can make sure that we actually get what we want here. So we'll say advanced collectible equals deploy and create. And that'll be our acting step. At the beginning, we'll do arrange. And then we'll do an assert of, we'll just check to see that the token counter has been increased. We'll do assert advanced collectible. The token counter is equal to 1. All right, great. So this will return our advanced collectible. However, we know that since we're actually going to be working with a mock VRF coordinator, if we look at our advanced collectible, we know that the bulk of the work actually comes in this fulfill randomness function. And we're going to have to tell our mock to actually return and call this function. So in order to do that, we should probably also return this creating transaction here so that we can get the request ID. Remember how in our lottery, we actually just directly called everything. And we needed this request ID to call this callback with randomness function. In our tests here, we're actually using our scripts a little bit. So we could either just go ahead and write out all the steps similar to what we did in the lottery, or we could adjust our scripts a little bit. For simplicity here, we're just going to go ahead and have this deploy and create function also return the creating transaction. This way, we can go ahead and get the request ID. So back in our test here, that means we have to do deploy and create equals advanced collectible and creation transaction. Now that we have this creation transaction, we can use it to get our events. And again, if we look back in our advanced collectible, we can see here that we're emitting this requested collectible with request ID. So we can go ahead and do request ID equals creation transaction dot events. We'll add the name of our event here, which is requested collectible, and then we'll get that request ID. Once we have this request ID, we can then go ahead and grab the VRF coordinator. So from our scripts, we'll grab this get contract, and we've coded our get contract in a way that if the mock has already been deployed, again, if we go back to our helpful scripts, if the contract has already been deployed, then we're just going to go ahead and grab it. So since here, our mock will have already been deployed, so we don't have to redeploy it. So we can just do get contract VRF coordinator dot callback with randomness, and we'll use the request ID. We'll pick some number like 777. We'll give it to the address of our advanced collectible. And remember, we're going to be calling the callback with randomness. This is what a real Chainlink node is actually going to call back. And it just needs the request ID, the randomness number, and a consumer contract. So request ID, random number, and then the consumer contract. And then, of course, we have to do a from account, from get account. And we'll import get account as well. And now we can move into our assert phase. So first, if this is correct, then our token counter should be at least 1. So we can assert advanced collectible dot token counter is greater than 0. Or we can be a little bit more specific here, equals 1. We also should technically be able to get the breed and figure out the breed of this first token, of this first collectible. Let's go ahead and parameterize this 777. We'll call it random number equals 777. We'll place that here. And then what we can do is we can say assert advanced collectible dot token ID to breed of 0, right? In our fulfill randomness, we're going to assign the token ID to being the breed. And the breed is going to be this random number mod 3. So in our test, we can say the token ID to breed of dog 0 is going to be equal to random number mod 3. And this is pretty much our full test. So let's go ahead and run this. We can do that test with -k. Whoops, it looks like our simple test has actually got an error now. We're getting this module not found. No module named scripts.deploy.create. This now, since we actually changed it, is going to be scripts.simple collectible.deploy and create. So now if we rerun our test, we'll see Brownie isn't going to error out anymore. So even though we skipped this test, Brownie still compiles it to make sure that everything makes sense. But what we see here is fantastic. Our advanced collectible unit test has worked perfectly. Let's go ahead and make an integration test for our advanced collectible here. So now we'll have our test folder here, and we'll have unit, and we'll have integration. Our integration test is actually going to look really similar to our advanced collectible here. So I'm just going to go ahead and copy everything. New file, test, advanced collectible, integration.py. And we'll just paste everything in here. Now, the only thing that we're going to have to change is that we're not going to be the ones to call back with randomness here. So we can remove this part. We also don't need the request ID anymore since the chain link node is going to be responding. This means that the breed that we're going to get is actually going to be random. So we can get rid of that assert as well. All we need to do is wait for the transaction to get called back. So we're going to import time. And instead of us calling back with randomness, we're just going to do time.sleep. Then we'll wait 60 seconds. Test can create collectible. We should also give this a different name. Integration. Now we should be able to test this on a Rinkeby chain, and our token counter should indeed increase with the chain link node actually responding. So now we can run Brownie test -k, just that test, --network Rinkeby. Oh, whoops. Right now we're skipping this because we're saying only for local testing. Now, since this is going to be our integration test, we're going to do the opposite. If network.showActive is in these local blockchain environments, then we're going to skip it and say only for integration testing. All right, great. So now we have a quick and dirty integration test that we can run. We're not going to run it for now because we're going to be working a lot with this Rinkeby chain and we're going to be deploying a lot of different things. And we don't want to wait so long. So this is fantastic. We have a way to deploy this. We have a way to get these new collectible tokens and create them. But if we were to take this address right now and try to view this token on something like OpenSea, we would get nothing back. We wouldn't get any result. Right now, our token doesn't have a way to be viewed or be visible by everybody else. These NFT platforms don't know what they look like. And again, this is where that set token URI is going to come into play. So we have to figure out a way to host an image and host all the metadata for our token URI. And the way that we're going to do this is by using IPFS. And this is a lot better than actually hosting this on our own server because anybody can then go ahead and host this image or this metadata themselves. Now there's further improvements to this with something like Filecoin, where you actually pay to have your image hosted forever. However, IPFS can hook into Filecoin in the future and is going to be a good enough solution for what we're looking to do here. Just keep in mind that what we do not want to do is run this on a centralized server. When we spin up our IPFS node we will be the only node that actually runs and actually hosts our image. However, the image is open for anyone to pin to their nodes as well. So it's much easier for us to host our images in a decentralized manner. What's bad, obviously, is if we just had the image stored on our own centralized server, because if our server goes down, then that URL no longer exists. If at least one node on the IPFS network is hosting this image, it will be available for anybody to see. So that's why it's going to be a much better solution than some centralized server. As I mentioned, decentralized storage is a topic that's getting better and better, and we're looking forward to seeing more and more ways to interact with them. In any case, we need to create an IPFS node that's going to host some data that looks like this. Or, like what we saw with our simple collectible, it needs to host metadata that will look like this. We both have to host a metadata file and an image URI file, which will host the actual image. Both of these need to be stored on IPFS. So let's go ahead and create a new script called create metadata, which will read off-chain and create our metadata file. So we'll start our scripts, per usual, with def main. And we'll get the most recently deployed advanced collectible using this -1 syntax. Of course, we're going to do from brownie import advanced collectible. Once we have this advanced collectible, we can then loop through all of the tokens and actually figure out the metadata for each one of them. So we'll do number of advanced collectibles equals advanced collectible dot token counter. Because we want this create metadata to create the metadata for every single token that we've created. Do a quick print line here, just saying print, you have created number of collectibles. We even run this really quick. Brownie run scripts, advanced, create metadata, network rinkb. Since we've already run this on the rinkb chain, we'll see you've created one collectible. If I were to run our create collectible script again, and then our create metadata script, we'd of course get more. But right now we only have one collectible. Now let's loop through all these collectibles and create their metadata. So we're going to create that file that looks like this, and it's going to have the name, which is going to be based off of the random breed that I got. It's going to have the description, which is based off of, again, the random breed that I got. It's going to have an image, which will also be based on the random breed that I got. And I just put some attributes in here, but again, these attributes. So we're going to say for each token ID in the range of number of advanced collectibles, for each one of these advanced collectibles, first we need to get the breed. So we're going to say the breed. The breed is going to be equal to advanced collectible dot token ID to breed of the token ID. Now, advanced collectible dot token ID to breed, this is going to return an integer, right? Because again, in our advanced collectible, this enum breed is going to be 0, 1, or 2. So we actually want to create a quick mapping that represents that 0 is Pug, 1 is Shiba Inu, and 2 is St. Bernard. So I actually like to create this in a helpful script called def get breed. And then it takes as an input, it takes a breed number, and it uses a switch statement. So up top, we'll say breed mapping equals 0 is going to be Pug, 1 is going to be Shiba Inu, and 2 is going to be St. Bernard. So in this get breed function now, we can just do return breed mapping of that breed number that we get. So instead of doing advanced collectible, the token ID to breed, we can now just do get breed. And this will return the number, and this will return the actual string. So we can just do from scripts dot helpful scripts import get breed. Now that we have the breed, we can start creating this metadata file. Now, what we're going to want to do is we're going to want to have some type of format for our contract to always pull from. So what I like to do here is I'll create a new folder called metadata. And in this folder, I'll have a new file. Called sample metadata.py. And then I just have metadata template equals, and then I just have this template that we're always going to use. Now in here, we're going to need a name, and then we're going to leave the name blank because we're going to want to fix it later. We're going to have a description, which we're also going to leave blank for now. We're going to have that image URI, which we'll also leave blank. And then we're going to have some attributes, which should be blank for this dog because we don't actually have any on-chain attributes, but I'm just going to go ahead and add some to show you what you could do if you wanted to give your dog some stats. You know, maybe cuteness, maybe raw power, maybe speed, agility, you know, whatever you want to do. So we'll do trait type, gonna be cuteness, and then value is going to be 100. This would basically say, hey, there's a trait type called cuteness, and the value of that is 100. So the cuteness of the dog is 100. So now once we have this sample metadata file, we can import this into our script here. So we'll say from metadata dot sample metadata import metadata template. And another quick note, you might have to put a __init__.py file in that metadata folder if you're working on older versions of Python. And we can start creating our new metadata file for this breed, for this dog. We'll want to save each collectible under their network and with their token ID. So let's go ahead and create a new folder. We'll call it Rinkby, and this is where we'll save all of the Rinkby metadata for all these collectibles, for all these token IDs. Now, before we actually save it though, we should just check to make sure that the file doesn't already exist, right? Because if the file already exists, that means we've already created the metadata for that token and we don't need to. So we can just go ahead and get the metadata file name, which is going to be equal to /metadata /network.show active. Of course, this means we need to import network from Brownie / the token ID with a hyphen with the breed.json. Just to make sure we're doing this right, we can even just print this out. Do a quick manual test. Brownie runs scripts, advanced, create metadata, network Rinkby. So this will be the name of the file. So metadata, Rinkby, token ID, and then the breed.json. Okay, cool. Now we can actually check this to see if this already exists. And we're going to use a Python library called path. So we're going to say from pathlib import path. And we're going to say if that path, this metadata file name .exists, if that path exists, we'll do a quick print saying metadata file name already exists. Delete it to overwrite. This way we won't accidentally overwrite metadata that we've already created and do extra work. So if it exists, we'll print that out. Great. Otherwise, we can go ahead and printf, creating metadata file name. We can even run this real quick. Great, you have one collectible, creating metadata file. Perfect. So let's go ahead and start creating this metadata file. So we're gonna have to give it a name, description, image URI, and we're not gonna give it any attributes though. So just name, description, and image URI. So name is easy enough. Since this is a dictionary or a mapping in Python, we can actually just go ahead and start mapping. So up above before this if, we'll do collectible metadata. It's going to be equal to this template. So this is going to be where we store all of our metadata. And We'll say collectible metadata of name is just going to be the breed. So if it's a pug, the name will be pug. If it's a Shiba Inu, name will be Shiba Inu. If it's St. Bernard, name will be St. Bernard. And we'll give it collection metadata description is going to be equal to, we're going to do an F string here, and adorable breed. Now, if we print out this collectible metadata, we should see at least the start of the metadata, which we do. Great. Name, St. Bernard, description, and adorable St. Bernard pup. Of course, you'll have a different random breed, but it should look something like this. Now, we're going to need collectible metadata image URI. This is where we're going to have our image already uploaded to IPFS so we can assign it to our metadata here. So how are we going to do this? Well, we're probably going to need some upload to IPFS function that's going to return our image URI. And then we can just set that image URI to the collectible metadata of image. So let's go ahead and start doing that. Let's create our upload to IPFS function. Now, in order to upload to IPFS, we of course need to have the images ourselves. I already have them downloaded here. And again, you can download them right from the GitHub yourselves if you like. To make this a little bit generic, we'll have this upload to IPFS take a file path. That way we can pass this image URI upload to IPFS. We're going to give it some type of file path here. We're going to have to grab that image path. So we'll grab that image file name by just doing breed dot lower, because right now our breeds are all uppercase. So we're going to want to make it lowercase. Then we're going to replace the underscores with hyphens .png. So we'll say plus .png. And then, you know what, let's just go ahead and add the full path here. So we'll say /image / plus breed.lower. Perfect. So, and then we'll even change this to image path. And then we can pass this to our upload to IPFS. So this file path now is going to be the location of the object that we're going to upload to IPFS. We're going to use this path library to actually grab that path to upload it to IPFS. So we're going to say with path file path dot open RB as file path. Now this is a little bit of sophisticated Python here. What we're doing is we're taking this path here, we're opening the file. RB means we're going to open it in binary. Since these are images, that's how we're going to actually open it, and we're going to upload the binary actually to IPFS. And then as FP, so we're saying this opened file is going to be named FP or file path. We're going to do image binary equals fp.read. And that's how we actually read the whole binary. And now this whole image is stored as binary in this image binary here. Now here's where we're going to do the upload stuff. Now to get started here, we're actually going to have to download the command line for IPFS. Download command line IPFS. We'll come right to the docs here. And again, there's going to be a link in that GitHub. And in here, there are instructions to download it for whatever system that you're working on, right? If you're working on Windows, if you're on Linux, if you're on Mac, these are the different ways to actually download this IPFS command line. You'll know you've done it right if you can type IPFS -- version, and you see something like IPFS version 0.9.0. It's important to note that we could also do the IPFS download desktop, and we could download the desktop version of this, and we'd see a user interface which looks something like this. We could upload our files manually and then manually go ahead and grab those files and place it into our scripts. But we're engineers, we want to do this programmatically. In any case, once we have this API downloaded, we can actually follow the documentation here, the HTTP API reference for actually uploading our code. We're going to be mainly working with this endpoint API v0/add, as this is the endpoint that's actually going to add our file or directory to IPFS. Now, what we're going to want to do is we're going to actually upload our images to our own IPFS node. We can run our own IPFS node by doing IPFS daemon. And we'll see an output that looks something like this. We can even see a web UI using this web UI URL here. This will look similar to what the IPFS desktop looks like. But again, we're going to work just mainly from this daemon from our own IPFS node. Congratulations, you're running your own IPFS node right now. As you can see, it's currently running on our own local host right here, HTTP 127.0.0.1 at port 5001. So to actually upload this, we first need to get that IPFS URL, which is going to be equal to this URL right here. Paste. Now we want to make an API call or a post request to this endpoint using this API v0 add. And these are all the different parameters that this add can actually take in so that we can actually post it to IPFS. For those of you familiar with curl and you want to test this out using a curl, I've added a curl into this create metadata file as a comment so that you can actually go ahead and test this if you want to use this. Now what we're going to want to do to keep working with our scripts is you should have like a little plus button somewhere on your VS Code. We're going to hit that plus button, and now we're actually going to have two different shells. One which is running our IPFS node, and one which is running our bash or ZCH or whatever other shell that your OS natively works with. Now that we have this IPFS URL, we're going to grab the endpoint, which is going to be, again, this right here, -API -v0 add, and we can make a post request to it. So for us to do that, we're going to say response equals requests.post. We're going to do the IPFS URL plus the endpoint, and we're going to say the files that we're going to upload is going to be equal to file image binary. Requests is a Python package that we're going to import. So we're just going to say import requests. Now, if we go back to the IPFS documentation, we can scroll down to see what the response looks like. It's going to return a bytes, a hash, a name, and a size. Now, if we look at this sample token URI, we can see the API call here. IPFS stores all its data using a hash. And if we're looking at this, the simple collectible, this hash here is the hash that represents this pug.json file. Everything in IPFS gets hashed, and every single piece of data has a unique hash, which is why it's so fantastic. If we were to change anything with this image, this hash would be drastically different. All we need to do is get the hash that IPFS gives the image that we upload, and we can go ahead and plug it into a template URL like this one here. So what we're going to do then is we're going to say IPFS hash is going to be equal to this response.json, since we're just going to JSONify the response to make it look like this response here. And we're going to grab that hash, right? Since it's going to return this dictionary. And we just want the hash here. Then we're going to give it a file name by saying it's going to be that file path dot split. We're going to do some fancy Python stuff here. We're going to say -1 to 0, which basically all this line is doing is saying, you know, if we have ./image/pug.png, we're going to we're going to split it up by these slashes into an array, and we're going to grab the last part of the array. So we're basically just changing this to this with this line right here. Then with this, we can get the image URI, which is going to be equal to an f string again, https ipfs.io/ipfs/ipfs hash file name equals file name. And it's this format right here which will give us this. So if I go ahead and even just copy paste this under as a comment to show you guys, we see this part's exactly the same. And then this is that hash here, represented here. And then we have file name equals, and then the file name. So excuse me, this is actually going to be like 0-pug. And that's exactly what we need. We need this image URI. So we'll do a quick print image URI. And then we'll go ahead and return the image URI. Now, since we're actually going to be testing this with